Our next talk will be by Grisha. So it's very nice to have Grisha back in Princeton. And today he's going to tell us about numerical analysis of the Young-Lee critical quantum.
All right. Thank you so much for inviting me. Thanks to organizers. It's a pleasure to be back at Princeton. So I'm going to talk about just the simplest non-unitary model, which Igor mentioned in his talk. And this is actually a work in progress with my student, Eric Arguella Cruz, Igor, and Yuan Shin, who is a postdoc now at CMU, but soon moving to a faculty position. All right, so let me start with some motivation. So, okay, with a plan. So I'm first going to talk about motivation and introduction of Young-Lee criticality. Then I'm going to talk about circles of control. Basically, it's circles of 2D Young-Lee model, quantum Young-Lee model, and how we can analyze it numerically using density matrix normalization group. And in this case, everything is very precise, and that's why it's control. And then I'll finally talk about spheres of influence, where we try to put this model on Platonic solids, and finally use this new beautiful method, which is called the quasi-sphere, and look for a critical point there. So let me start with the motivation. As Igor mentioned, there are a variety of minimal models which were discovered by Belavin, Polakov, Zamolodchikov, and most of them are actually non-unitary models. And whether we know a lot about unitary models, we don't really know much about non-unitary models, and whether they have higher dimensional analogs, particularly in 3 dimensions. And just give you a list of first few non-unitary minimal. There's this M25, which is a Young-Lee model. It's the simplest non-unitary model. It's actually the simplest minimal model because it has only two primary fields: identity with dimension 0 and primary field phi with dimension conformal dimension -1/5 and negative central charge. But there are other unitary minimal models, for example, M27, which has 2 primary fields with negative dimension and identity: M29, M35, M37, M38, which Igor discussed in his talk, and infinitely many more. And for some of these models, there are various proposals for their Ginzburg-Landau description or microscopic description, but so far it's a bit vague. On the microscopic side, I think there's a proposal for M27, well, for M25, which I'm going to talk about. But ultimately, I think once we would like to verify maybe numerically this proposal for M38, and just as you mentioned, epsilon expansion, even if it's computed to 5 loops, it's still well, we can't really be certain about this. So it would be nice to check it, to test this numerically, experimentally. So we don't have conformal collider yet. So maybe it's so far we just can rely on numerical experiment. And yeah, this is the papers. Some few of the papers were field theoretical Landau-Ginzburg descriptions, and microscopic descriptions were developed. And I'm going to talk about just the simplest non-unitary model. And let me just give you a short introduction. So there was this seminal paper by Yang and Lee in 1952, where they studied zeros of the partition function of the Ising model, ferromagnetic Ising model, across different dimensions. And they studied this partition function of the Ising model as a function of complex magnetic field. And they found, and they proved it mathematically rigorously. Well, they have a theorem in their paper that for the Ising model, the zeros of this partition function lie on the complex axis of magnetic field. And if you have a finite number of spins, there are these zeros. So if you go to thermodynamic limit, the zeros become denser and denser, and then become branch cuts. So which start from H critical or minus H critical. And so, right. And the idea was in their paper that, first of all, I will mention that this is a picture in a paramagnetic phase or in disordered phase. So it's where T temperature is bigger than critical QD temperature. And the idea of this paper was if you cool your system, if you reduce your temperature, this branch guts, they will become closer and closer to real axis. And because of that, you're going to find some non-analyticity in your free energy and thermodynamic properties of the specific heat. So if you're in the paramagnetic phase, the solar phase, the branch guts are away from this real axis, but they move closer once you converge to the critical point of your Ising model. And actually, almost 20 years later, Cortman and Griffiths, they look for density of the zeros near this critical point. And they did it numerically. They used high temperature series expansion, where they, I think, they literally compute this partition function as a polynomial of actually e to the IH, and then just try to see what are the zeros of this polynomial. Well, we know they lie on the complex plane, but what are the density of the zeros? And they noticed that there's a scaling of the zeros. In 1D, you can solve exactly, but in 2D, they did this numerics. And they noticed that actually this density of the zeros near this critical point diverges. Diverges in 2D, but actually decays in 3D. And there's some scaling exponents which you can assign to this behavior of this density of zeros. So the density of zeros of this at the imaginary magnetic field behaves as h minus h critical to some scaling exponent sigma, which they can estimate from this numerical analysis. And then 7 years later, Michael Fisher suggested that singularity near this H critical can be described by 5-cube model with imaginary coupling, which Igor already mentioned. So we have to tune imaginary magnetic field to this critical value, and then we have this critical 5-cube theory. And this 5-cube interaction is exactly marginal in 6 dimensions. So Michael Fisher developed 6 minus epsilon expansion. So we shoot from 6 minus epsilon down to 2D, or in 1D we know exact answer again because we can compute this exactly, but we can shoot from 6 minus epsilon to 1 and estimate anomalous dimension of this phi field. And anomalous dimension of phi field is related to this density of zeros, sigma, to some hyperscaling relations. And actually 7 years later, after Michael Fisher, Cardy basically said that this phi cube in 2 dimension is actually M25 model, which we know from BPZ paper. And therefore, we know this anomalous dimensions exactly, and they are this dimension of phi. And then we can go and compute 3-point function of this primary field phi, and that's proportional to structure constant, which is purely complex, as Igor mentioned in his talk. And then we can, Cardy listed a 4-point function, which is related to conformal blocks, and then it's related to hypergeometric functions of cross ratios. And also is that it's true if we normalize 2-point function by 1. And what is bizarre about this model is because the anomalous dimension is negative of this primary field phi, correlation function grows in distance, and that's very counterintuitive feature. It's hard to believe that something grows with correlation grows with distance. And I don't know why Cardy put this sign of equality. Maybe there's some confusion going on at that time. But yeah, all right. So I'm going to talk about this correlation function today. So and as you mentioned, people pushed this to 5 loops already. And this paper by Barinsky, Gracie, Kompaniets, and Schnetz in 2001. So this is just the beta function to 5 loops. And they have this nice plots in their paper where, again, they shoot from 6 minus epsilon to 2D, 1D. Actually, they go from left to right now. They change parity with previous Fisher plot. But and then you can estimate from there have many methods. They have different summation methods and so on. And most of this method, on average, they give anomalous dimension in 3D, which is already positive. And sigma, this scaling dimension of zeros, is also positive, so it's in agreement with a previous paper by Portman and Griffiths. So it's in Fiji, it's already positive, but it's small. It's 0.21, so it's positive, but it's small. And they also computed you get omega scaling exponent, which is anomalous dimension of 5 cube operator, and it's around 4.5. And there's also again like more high temperature resummation series paper by these people. They went to very high order in expanding this partition function in a polynomial, and they pretty much agree with this result, with the scaling exponent of phi. So I think we got quite confident from this results that the scaling exponent of phi field should be around this number. And also there's actually one bootstrap paper by Golitsa and Raga, where again, I don't really know how people do bootstrap for, if it's possible to do really bootstrap for non-unitary model, but they have a result which is also close to this.
Okay, the equation.
Yeah. So I think Johan knows much better how it's possible. Yeah. And recently there was a paper by Simone, Mina, and Andrei, Igor, and Zima about sphere free energy for this model up to 3 loops, and that's a result which they got. It's a positive number. So, and hopefully we didn't check it, but hopefully it can be checked by fuzzy sphere technique as it was done for the Ising model. All right. So why so okay? So let me start with quantum to the Young-Lee model. I call it circles of control because we work on a circle, and my talk will be very complementary to the first talk today by Andreas, because I basically study basically have exactly the same Hamiltonian as Andreas has in his slides. The only difference is that there's an I here in front of magnetic field, and so it's an imaginary field. So what we do, we study this what's called transverse field Ising model, quantum Ising model on a circle. And we have to be in the paramagnetic phase, so we take Hx as a transverse magnetic field. So we make it's Hx is large, so we are in a paramagnetic phase, and then from paramagnetic phase we go up to the complex magnetic field, tuning this Ag with the I constant, and X and Z are Pauli matrices. And this lattice model doesn't have now Z2 symmetry as the Ising model has, but it has this so-called PT symmetry, which Igor mentioned. Which is basically this again Z2 operator, so it's anti-commutes with Pauli matrix, with Phillips Pauli matrix Z. But I mean, so that sign is that term is not invariant under this P spin symmetry. But there's also, to fix this, there's also this complex conjugation symmetry which flips I to minus I. So, and because of the symmetry, so the Hamiltonian is not Hermitian anymore. As an Ising model, but it's PT symmetric, and because of this PT symmetry, you know that our spectrum of this Hamiltonian has either real eigenvalues or complex conjugate pairs. So that fixes this spectrum, and you know that if your imaginary complex magnetic field is small, then you should start with real eigenvalues, because you know the Ising model was Hermitian; it had only real eigenvalues, but once you perturb it a little bit, the spectrum will be real. And the only way to get this complex conjugate pair is 2 real eigenvalues will merge at some point. And actually, this merging point is the critical point for this Young-Lee model. So okay, so so it was first studied in the paper by von Galen in 91 and 94, exactly this model. And from this paper, you can see that there is a line of critical points because as the Young-Lee edge criticality is there for any paramagnetic at any paramagnetic temperature, at any temperature bigger than critical. So you just need to set any temperature bigger than critical temperature, then go to complex magnetic field, and then you will see Young-Lee edge, and therefore there's this line of critical points, if you wish. Which I now plot as 1 over Hx. So when Hx is bigger than 1, we are in the paramagnetic phase, and when Hx is 1, we are at the Ising CFT. And then So we have to be in paramagnetic phase, in disorder phase, so hx has to be bigger than 1, or 1 over hx has to be less than 1, so we can say we'll be somewhere here, and then we turn on magnetic, imaginary magnetic field, and this line separates what we call PT preserved phase and PT broken. And if we look, say, at the spectrum, so we can draw the spectrum of this Hamiltonian along this line, starting with Ising in paramagnetic phase. That's the spectrum. So it starts with some real numbers, which here they're Ising spectrum of the Ising model. So this is just for n equals 26. I don't know. Surprisingly, it's agreed with the same n, which is today in the morning. And the levels they go into, they stay real, but at some point they merge and go into complex and split into a pair of complex numbers. And that's where we say that the PT symmetry is broken. And that's what we can call pseudo-critical point of Young-Green model, right? So this is pseudo-critical point. But to get thermodynamic critical point, we need to see how this pseudo-critical point extend into thermodynamic limits. So we have to take n goes to infinity, and that's how we get thermodynamic critical point in this. So that's how this criticality works in 2D. Right. So before I go into results, I just want to mention that the way we can study this numerically is again using what's called density matrix normalization group. And in this case, so okay, I'll just want to mention what it is. So the idea is to, if you're solving some quantum system with n qubits, you can approximate many-body quantum state, which has 2 n parameters, by what is now called matrix product state. This was an original idea by Stephen White. So the wave function, the wave state is approximated by the product of matrices, which are called MPS matrices. They're these matrices L and R, and they have roughly m by m size. And so basically you approximate the 2 to the n parameters by polynomial number of parameters in n and m squared. And this approximation works extremely well in this one-dimensional quantum model because it is sensitive to entanglement. The size of this matrices you take depends on entanglement entropy between subsystems, but for 1D there's a theorem that for gap systems it's bounded, so it works really well. For CFT it works a little bit worse, but it still works extremely well. And in this talk, I just want to mention that people in condensed matter, they studied non-Hermitian systems using density matrix normalization group since basically the beginning of density matrix normalization group. So it's actually no problem for DMRG to study this non-unitary, this particular non-unitary models. In this case, in the Young-Green model, our Hamiltonian is not Hermitian. Therefore, we have to define right eigenvectors of the Hamiltonian and left eigenvectors of the Hamiltonian. We still define bra states as a Hermitian conjugate of bra left states as a Hermitian conjugate of ket left states, and bra right states Hermitian conjugate of right ket states. And left and right, they are orthogonal with each other if they belong to different energy levels. But right with right is not orthogonal. Left with left is not orthogonal. So there's this peculiarity about non-Hermitian Hamiltonians. And as I said, people from condensed matter knew how to use density matrix normalization group for this type of models. You need to properly build this density matrix now. And actually, there's a freedom of building density matrix, and one of the way we chose it was I think originally this paper by Kondev and Marston in '97. So if you build density matrix for left block using this right and left eigenstates this way, it works really nice. And basically this density matrix defines MPS matrix for you.
So, sorry, one question. So at the PT symmetry breaking point, is that possible? I think there could be the 2 eigenstates become the same. They merge.
Yes.
The Hamiltonian is not that lethable, right?
They do merge exactly when you, they do
How
merge.
to deal with using this? Because it seems to assume that different A is
So
different.
so you're basically asking how does it work when you go into
Yeah.
levels? First of all, the short answer, we don't need it because we actually always just need to find where they merge. We don't really need to go beyond. But I think practically it just works. So you just can see that, well, okay, I didn't really thought about it deeply, but it works. Yes.
So eigenstates merge or only eigenvalues?
No, eigenvalues merge. No,
Eigenstates.
there are two different eigenstates, right? And they are related by each other by PT symmetry, but eigenvalues are complex conjugate pairs, and at this point they are exactly when they merge, they're exactly equal, so they're exactly degenerate, but there are two eigenstates for one.
Not more.
Yeah,
So
yeah.
eigenstate, you just don't know which one you found, right? Then the best is find two state.
I have a question.
Mhm.
Yes, so when you say that the two eigenstate merges, like, do you mean the lowest level, two levels, or?
Oh, they merge the lowest two levels, and they are higher level. Like at the end, all levels will merge at some point.
So it's like a very non-trivial phenomenon because generally that's not true, right?
Yeah, I will show the spectrum. You'll see the like some pattern of merging levels. Yeah. Okay, so the Young-Lee model is not Hermitian, but the Hamiltonian is symmetric, and therefore left and right actually related by complex conjugate. And bra left is right is a ket right transpose. And therefore, well, and correlation function, if we need to compute correlation function in this model using left and right eigenstate. In this case, that's how we compute correlation functions. Okay, so before I go again in detail, so let me mention that we're using this idea of radial quantization. So we work on this, we work with a Hamiltonian on a circle, and there's this idea of finite size scaling is that gaps of energies that will go with size of the system is 1 over n, where delta n are anomalous dimensions, and a is called the speed of light of a quantum critical point. And that's what we're going to use to extract anomalous dimensions. And also there's an important point is that the way we tune this, the way we identify critical point in the system is using what we call criticality criteria, because there are infinitely many ways to define a pseudo-critical point, right? One way, which I said, is to say when the first two levels merge, and that's exactly the way it was used in the original papers by von Galen in 91. I think he used to define this pseudo-critical point as exactly where two first level merge, but it doesn't have, it's not the only way to define pseudo-critical point. There are infinitely many other ways, and another common way, which is called just finite size scaling way, is to say that is to just look at the point at the pseudo-critical, at the magnetic field and the complex magnetic field where the gap, the first gap, basically at the side of the system n is exactly equal to the first gap at the system n plus 1. So it gives you this criteria, this criticality criteria we're going to give you pseudo magnetic field, which you can then extrapolate to large n. And all of these methods, when extrapolated to thermodynamic limit, should give you exactly the same thermodynamic critical point. But working at finite n, you're not restricted to one method. There are infinitely many. In fact, I will show like we use several of them. Right. So to find thermodynamic critical magnetic field, we just extrapolate it to infinite n. And for non-unitary CFT, we know, for example, that what Igor mentioned already, that the ground energy scales with n linearly, but there's this correction which goes as 1 over n, and this is proportional to this effective central charge. And for effective central charge is the usual central charge minus 24 times minimum anomalous dimension, and in Young-Lee it's 2/5. And actually, this behavior makes it a bit difficult to distinguish different non-unitary models, because effective charges between those tables of non-unitary models, they have very small numerical difference. So okay, I don't have it, but some minimum models like M35 and M maybe 27, they have like 1,000 distinguish in their effect, 1 over 1,000 difference between their effective central charges. So that make it harder numerically to verify what the model we have on microscopically. All right, so so what are our result? But that results we obtained for smaller systems before in 91. So theoretically, we can look at M25 model. So we know these are two primary fields, identity and field phi, and we can construct all the descendants. And what is kind of remarkable about this model is that, so this is a table of descendants. So this axis is a spin, and this is an anomalous dimension. So we start with -2/5, which is phi, that's 0, which is identity. Then the next two descendants is d and d bar phi, and so on. So you can see actually that all of descendants up to this level, they are full derivatives, and that's this first kind of non-trivial non-derivative descendant is what I call Q, following this original paper by Yurov Zamolodchikov, who did conformal truncation approach to this model. And okay, so let's see what n equals 26 gives us. So we can look differently for different spin sectors, and if we look at spin 0, clearly see that taking this thermodynamic critical value of magnetic field and looking for states at this value, we can extract anomalous dimensions, which we need to properly normalize. But we clearly see, I just want to highlight that it works perfectly well in 2D. So we can clearly see that all the states, if we go to next spin, again, we can identify these states. You see, okay, so this question, so levels will merge at some point. Some levels merge faster, some earlier, some levels merge later, but most of them will merge at some point. And we look for these levels at the thermodynamic critical point, and that we're following this method by von Gelen. And all the states kind of agree nicely, and we can look for collection of them. So it's basically we have high precision of getting these anomalous dimensions numerically. And what we noticed is that actually to make numerics work better, we have to be deep in paramagnetic phase. If we're close to Ising model when hx is equals 1, it works much worse. So we have to be like deep into paramagnetic phase, and basically the deeper we go, the better convergence with CFT. And for example, just to show you that if we're close to Ising critical point, so if I take hx equals 1.25, you see there's already like the correspondence is already worse because, for example, TT bar merges with this state earlier than identity merges with primary state 5. So
sorry, just to confirm, because in general in the Hermitian system, there could exist a point that the level merge, but the eigenstates also merge. Is this just the level merge, but the eigenstate is still?
What do you mean eigenstates? When they're here on the green line, there are two eigenstates.
Yeah.
They have a complex conjugate eigenvalues.
Yeah,
they don't know. What do you mean? Like
yeah, but I mean at the critical point.
What do you mean merge? I mean they have at this merging point, the eigenvalues are exactly the same.
Yeah,
But there are
that's
two,
what I mean.
there are two eigenstates for one eigenvalue.
They look different. Or?
Yes, there are two
Okay.
different eigenstates. Yeah. Now, how much time do we have? Oh, okay, I'll rush a little bit. All right, so
Just a quick question. If you increase and you will see, no matter what hx you choose, you will emerge to 1 point, right?
if say this again.
If you choose larger n, even though you have a smaller hx, you will still get the good result.
Yeah, the
right?
larger the n, the better the picture. The
okay.
more
It's all
closer.
number, yeah,
Yeah.
okay.
So actually, that's the question. Like, how does it converge with n?
Oh,
And for example, we can look for this ratio of energy levels. So conformal field theory would predict that this ratio has to be 5. So it's this level derivative minus this divided by this gap has to be 5. And then we can see experimental, like numerically, that it converges to 5 with n to the 8/5 power. And this is because there are only, as I mentioned, all of these descendants, they're all full derivatives of primary operators. So only the first terms which contribute to finite size scaling correction are coming from this operator Q and TT bar. So that basically the lattice Young-Lee in 2D is this Young-Lee CFT normalized by the speed of light, plus these corrections which are coming only for this high level descendants Q and TT bar. Well, TT bar even slightly higher than Q, and therefore we see this power n8 thesis basically difference because this the dimension 2, so it's difference between their dimension 18th is minus 2. But here the point. So when we're close to Ising critical point, this coefficient in front of this term is extremely huge. So it's like, if you estimate it would be like 300, right? So it converges pretty fast with n, but the coefficient is really large, right? And if you go deep into paramagnetic phase, you can see that this coefficient becomes smaller and smaller. So that's why it's preferable to go numerically to go deep into paramagnetic phase to improve convergence. So if you that's the idea. In principle, you can be anywhere, but then you need to push n higher, right? That's the idea.
Is there some theoretical reason that you get this large number when it's close by?
I'm not aware. Yeah. We don't.
Diverges at the. HX goes to the critical point.
Yeah, I guess when we go, yeah, that's probably we know that it's bad to merge Young-Lee with CFT. So you don't want these two critical points to be right on top of each other, right? So that's kind of the heuristic.
You don't know how it diverges.
Oh, we don't know. Yeah, so we know it's big, but you know, it's like 300 when you're close to Ising CFT, but.
You can probably do some kind of scaling, right?
Yeah, everything you can scale.
Oh,
It's
yeah,
some
actually,
parallel divergence.
Yeah, actually, maybe right. Yeah. Right. Actually, good. Yeah, it's good.
Actual crossover phenomenon? I mean, how can it be that two CFTs don't want to be close together?
Yeah, I don't know. Yeah.
Well, you lose the other one at
Yeah.
HX equal 1, you just lose the other one right there.
Yeah, if you exactly at h equals 1 or you go in ferromagnetic phase, then there's no Young-Lee point there, right? It's like your edges, like your Young-Lee edge just collide, like it goes down and just collides to you.
It's a fixed point annihilation scenario or something. I mean, it's not.
Yeah, you lose this. If you look at even you see it in the semi-classical theory that there needs to be one sign and not the other. Yeah, so.
Okay, I have just 5 minutes. So okay, so that basically the anomalous dimensions were verified in this original paper by von Gehlen, and there were not much of work after those original papers in 91, 94. But what wasn't done is, I think we didn't find anything when like people looked for how actually lattice operators transform into this CFT fields in this flavor of this paper by Ijan, Milstead, and Vidal in 19. So we can actually assume that each lattice operator goes into CFT onto this primary operator plus descendants, and with some real numbers A1, A2, B1, B2, and this I here is, you need to put I here to make this PT odd, and there's no I here to make it PT even. And then, for example, you can see from here that if you compute matrix elements of these operators, you should expect this behavior. For example, you know that if you can extract 3-point function, which is purely complex, using this matrix elements of these operators, lattice operators, and you can get it with a really high accuracy. So you can see that the result matches with theoretical value up to 10 to the minus 4. So it's truly circles of control. So in this case, so we see everything. But what is more interesting is to go and look for a correlation function, because I was like, we were curious like whether the correlation really grows or not, like whether CFT predictions are correct or not. And okay, so you can take operator and then you can extract these correlation functions if you properly subtract some proper terms from this expansion. And from CFT, you would expect that, so the correlation function, which is written in Cardi's paper, it's a correlation function which uses vacua, and that grows with as a power. Sorry, using this identity operator, and identity operator is excited state, and the vacuum state is actually phi. So the correlation function with the ground state is a 4-point function of phi, and on a circle it has this form with hypergeometric function, and we checked that basically. Now we use the MRG results. So, okay, so here's plot for n equals 50 qubits, so it actually becomes very close to. We take h equals 2, and it becomes closer and closer to theoretical prediction where you have signed the power of 4/5. And we also checked this 4-point function, which is this crazy hypergeometric combination of hypergeometric functions. So it decays and you go very closely. So the CFT, so the upshot is that CFT works perfectly for this model. And I think we're, okay, so actually I'm out of time. I just want to highlight the fact that we can actually look for a flow between Ising and Yang-Li. So we can see how we know exactly, we control perfectly states in an Ising model, and which was already said in the first talk. So we know Ising critical point. And what we can do, we can plot spectrum in the favor, like people in Canvas matter like to plot bands. So we can plot spectrum along some lines. So we first go to ferromagnetic phase to paramagnetic phase of Ising, crossing Ising CFT, and then we go up into imaginary magnetic field, and then we can see how energy levels or how our states flow between those models. So if you wish, it's like a flow between Ising to Yang-Li. And there's some, okay, I don't know any theorem, but there's a pattern. For example, we can clearly see that stress energy tensor flows to stress energy tensor. Right, and we can identify things on both sides, so we know perfectly what state is what, right? And this is just a list of how things flow. For example, epsilon flows to box phi, right, in Ising model. And here in 2D, I flows to phi and sigma flows to I, which is a bit weird. So we would like to have maybe sigma to phi, I to phi, but there's there's no crossing, right? We would maybe expect crossing of levels, but there's not. And okay, this is how they merge. All right, let me just, okay, so it's out of time. I just briefly mentioned what we did for 3D. So now we can perfectly equipped to go to 3D. And first, there's this nice paper by Lau and Richkov, where we put Ising model on icosahedron, and there are papers by Richard Brower about this idea of putting things on platonic solids and discretizing them. And now we just, again, switch a magnetic field and look for this flow of states, and again, in Ising model, things are perfectly controlled due to this paper by Lau and Richko. So we know what states are what. So we can again identify. Now we don't really know what happens in 3D. So it's kind of a guess, but comparing it with 2D, we sort of can successfully identify states on icosahedron on this Yang-Li icosahedron. They look very much the same.
You got the I. Sigma is opposite.
Yeah, here I goes to I and sigma goes to phi, because now phi has positive anomalous dimension. So there's more natural here.
Okay, that's what you.
But I think what we use now, we assume that stress energy tensor flows to stress energy tensor. So we know where's the stress energy tensor in Ising side due to this paper, which basically tells us how to do it properly, how to identify states. And we assume that it does flow to stress energy tensor on Yang-Li side. And basically, okay, so in using icosahedron, we don't have finite size scaling in our hand because it's just n equals 12, just 12 sides. But we can fix speed of light, demanding that this t becomes free. We know that stress energy has to be exactly free at 3D. And we also demand that, for example, we can demand normalization condition that the difference between stress energy tensor and identity, which is free, divided by the difference between first descendant of phi operator, which is 1. The difference between phi and descendant of phi is actually 1. So fixing this to be free, we can get this pseudo critical line and measure phi at this critical line is pretty close to which we know from phi epsilon expansion. Okay, then we just for fun we play the same on the dodecahedron, which has 20 spins. The same picture. Higher levels slightly shuffle, so they're like higher levels become here outliers, but more or less things are the same. And if you do the same thing, you get even better delta phi. But finally, the true method here would be to go to this new beautiful method that phi is sphere, which we're going to hear about today more. And to basically, again, we just naively took the phi sphere Hamiltonian, add this imaginary magnetic field in the same flavor which we did before. This is two Haldanean prepotentials, spin-weighted harmonics, and this is the plot. So it's, all of them look very similar, but okay, I don't have time. So finally, just want to show that we did some finite size scaling analysis using different criticality criteria. We do see that we have thermodynamic critical point, and if we use the same criteria for stress energy tensor, we can see how delta phi flows with n number of electrons here, and just approximating by linear, very crude approximation, so very preliminary results, we get something which is 0.26, which is not far from what we have from 5 loops. So okay, let me conclude. So I just want to highlight that Young-Lee critical point in 2 and 3 dimensions is another fundamental CFT that can be studied and tested numerically, but currently lacks the same level of understanding as Ising model. So ideally, we'd like to have the same table which we saw before from David Simon Zaffin paper, but there's no such table for Young-Lee. There are no LPE, there are no, even first scaling dimension are really not known in 3D. But hopefully, like, using this fuzzy sphere, we can start filling plots in this paper. The other point which I want to make is that non-unitary minimal models in 2D and hopefully in 2D can be perfectly studied using density matrix normalization groups, so you can push it to really high n. Well, in 3D it's harder, of course, but in 2D it's perfectly fine. And fuzzy sphere is, of course, a very promising approach for Young-Lee model in this case, and other microscopic models, microscopic description for other non-unitary critical points has yet to be developed. So that's all right. Thank you.
Time for some questions. Yes.
There's some standard questions, like for the spin chain, you had 26. But is that the limit of what you can do?
That's a limit what I can do on my laptop. Yes,
Probably it was the same, but the 26 I showed in my talk,
but
I think you can do close to 40.
No, not for, no, for, I cannot do, we cannot do 40.
We can do.
I don't know, maybe you can do maybe we can push to 30. It's exact diagonalization, and maybe on the cluster can be pushed to, I can, I know you can push it to 40, or I cannot.
The question is whether it's useful, no, because you seem to say that so sometimes going to larger system really pays off, even if it's exponential. So I'm just wondering, do you think there's potential to learn kind of significantly more by pushing, or is it just like
I think yes, because basically, okay, so I feel it's important to push for higher, because basically what happens, for example, here, okay, I mean, it turns out that we can, okay, where's this plot? Where I have, where with this plot, right, for when we try to see the ratio of levels, and this is 5, I mean, we know that we can make this coefficient smaller if we go deeper into permeating phase, but okay, so there's no reason why it will become very small. It could still stay like 100, right? And for this type of levels, definitely we need higher n, right? So they kind of, if you use low n, you really like far away to see the convergence. So you really need to push higher. Like,
yeah, I don't think you can do exact at 2 to the 40. I mean, that's a huge matrix, okay? But you can do something.
No, it's only line. It uses lunches or nullity, so only like say first 100.
Well, that's right. I was going to say yes, but you can go to a huge matrix and get the low eigenvalues.
Right.
Matrix. And so presumably that's all you need, right?
Yeah, that's what I do. That's what I do.
Oh, so then you can push to large numbers. I mean, huge numbers, because you only need the
well, approach. If you do exact normalization, I don't know what's the current.
But I think our philosophy is if the problem is.
If you don't do exact diagonalization, you do matrix-free approach and you find the low eigenvalues.
But but
Yeah,
we call,
lasers, yeah.
but we call that exact diagonalization
That's
also.
what, that's,
In subspace, yes.
Yeah, but
Of course, yeah,
you
yeah.
can go to n equals 100,
Equally exact to doing the whole thing.
but not to n equals 100. So it's like n equals 40 maybe the limit, current state of the art.
I may say something. I think in this business, if the problem is important, and then you go to the maximum you need, and for some problems like on the Kagome, and in condensed we deem it important. We can do matrices of 10 to the 12, or at least close. No,
So
and then
n will be like 40, right?
yeah.
Yeah, n equals 40, but you
But
can
also
go.
there are symmetries. There's translation
Yeah,
event,
of
so the
course,
blocks
of
are
course,
actually
of course.
smaller. So
Yes,
perhaps
yes.
if the problem is really important, perhaps we can even do slightly beyond 40, and then we apply
Well,
for
maybe-
supercomputing time and do it there.
well, maybe in your program, you can just choose,
Yeah.
put in an I and see what.
Yeah. Yeah, because I think actually our fuzzy sphere code uses artpack.
Right,
So if actually that runs out of the box, tomorrow I have some results for you if you want.
Uh-huh.
Maybe we should leave more questions for discussion.
I think.
Okay, just.
So what was the main feature, the main difference due to the non-unitary net?
In terms of,
But in this study, right?
so basically from finite size scaling analysis, there wasn't much in feature for non-unitary to comparison to unitary. So you would do the same energy levels and see that energy levels give you conformal states, and you would do exactly the same in Ising model and see that energy levels give you the.
Energy levels are still real.
Yeah, energy levels are still real because you always look for slightly below the merging point. So energy levels are still real. So it's just, but at the point, basically, it's perfectly can be studied numerically. Somehow it wasn't really studied before.
So on the sphere and the quantum Hall problem, there's some interesting cases where you can map some of these frustration-free models come from Jack polynomials, which Jimbo and Miwa studied, and they all relate to Virasoro algebras, and all the ones that relate to the standard quantum Hall states, of course, are unitary. But there's actually some exact models which have a frustration-free ground state, which corresponds to a non-unitary CFT, one of the minimal models. And it appears to be it's called a Gaffnian. It appears to be a transition between two different quantum Hall states with a different kind of essential parity, but there's no change in the Virasoro algebra at the end. At least there's no change in C, right? The anomaly, but it has the corresponding field theory has a single non-negative weight primary field, which seems to relate to the point of attachment to the boundary of the domain wall between these two different things. But since they have opposite parities, the bulk at this critical point, it's not known whether it's z equals 1 criticality or something else. There's a very strange critical point. So I just wondered if
I thought people were saying Gaffnian is some F3 file or something.
yeah, that's the minimal classification. But again, a very interesting physical question about what exactly is the nature of the criticality, because from this viewpoint, there's nothing special about that. But from the quantum Hall viewpoint, there's certainly a huge amount, because it implies that the edge theory is not bound to the edge, it's leaked into the boundary.
Yeah, from physical point, definitely they're completely bizarre, right? Correlations grow, and so it's from numerical point, they're like the same, almost.
Okay, let's thank Grisha again for writing.